Swayam Prabha. Digital India. Educated India.
So, welcome to this lab session of the course Elements of Mechanical Vibration. We are going to start with a very simple free vibration apparatus, which is going to give us a glimpse of a simple free vibration response of a mechanical system. Now, the system that we have is a simple oscillating beam, which you can notice here. If I can perturb this is the beam on which a motor is mounted at this position, and the beam is actually hinged at this end. Okay. So, there is a bearing at which the beam is fulcrum, and the beam can therefore swing about this end. Okay. So, there is no restraint at this side, and the beam is actually making a rigid body oscillation. Now, apart from this mass which is fixed at this location on the beam is hung by a helical coil spring, as you notice here. So, the spring is fixed at this end and it is connected to the beam, the tip of the beam at this end. Okay. So, this is the simplest of the vibratory system, consisting of mass and spring. And unlike a typical spring mass system wherein we have a vertical translatory vibratory motion, this one is an angular vibration. Okay. So, the beam is swinging about this point. So, the beam executes an angular vibration. Okay. So, this simple vibratory system I can represent by this simple beam which is hinged at one end. So, I can show it hinged here. The mass of that motor at an appropriate location as it is given. So, maybe this distance is A, and the beam is supported at its tip by a helical coil spring. So, that I am representing as K. So, this beam swings back and forth, and while doing that, there is a continuous interchange of the kinetic energy and the strain energy, potential energy in the form of the strain energy in this case. So, the string will get stretched or get compressed as the beam swings about its mean equilibrium position. Okay. And the mass of the motor here is going to store much of the kinetic energy of the system. Now, this beam being hinged here, and for that small oscillations that are taking place, the beam is expected not to undergo any bending. Okay. So, the beam behaves like a rigid beam, and so therefore, the mass of the beam may also store some part of the kinetic energy. At the moment, if you want to make a simplistic estimate of the natural frequency, we can treat this system to have a mass which is lumped at this location, and the beam mass may be neglected, and all the strain energy stored in the spring which you can see there, the helical coil spring. And then it is quite obvious that you can get a free body diagram and find out the natural frequency of this system. All right. So, that part of course is left to you as an exercise. We will give you the value of the mass of the motor. So, we will give you the necessary dimensions and the other details like mass of the motor, the stiffness of the spring, and also we can give you the dimensions of the beam, so that the mass of the beam, if you want to include in the estimation of the natural frequency, that also can be included. Now, therefore, when as we discussed in the theory, the modeling of the actual physical system into its equivalent vibratory model, you need to make some assumptions. Now, here as a first approximation, you can assume that the beam is comparatively, the mass of the beam may be comparatively smaller as compared to the mass of the motor, and therefore, the inertia associated with the with the beam may be neglected as a first approximation. If you want to include the mass of the beam, then it will get added up to the inertia. Okay. So, then in that case, if I write the governing equation of motion as I theta double dot, which is going to be the value of I of this beam, and I can add to this mass moment of inertia of the beam the inertia because of the motor mass, and therefore, I can use m a square as the total inertia. Okay. And this of course, will be the other term that is expected is going to be this term because of the spring, and that spring is going to create a restoring torque or restoring moment about this fulcrum, and therefore, if this distance is taken as b, then this is going to be k b theta, and the distance will be again make it b square. So, that is equal to 0, and therefore, the natural frequency from this expression can be obtained as square root of k b square over I plus m a square, where m is the mass of the motor. It is of course presumed lumped at this point, where it is mounted on the beam, a is the position of it, and I is the mass moment of inertia of the beam. So, based on the dimensions and the material, you can find out the value of I, k the spring rate of that spring which is holding the beam at the tip, that also is known, and the position of that contact the position of the point at which it is connected is also known. So, everything is known here to find out the natural frequency. Now, that is the theoretical part. Experimentally, how do I find the natural frequency? Now, you can see that if I perturb it, just like we discussed in the first topic, that I give an initial displacement and then release it. So, it is like x naught is given some value, and v naught, the initial velocity, is 0 at time t is equal to 0. Once we give that initial disturbance and then release it, the whole system vibrates naturally at its period of oscillation. So, the free vibration natural frequency is what we observe here happening. Now, we will be of course interested in not only knowing the natural frequency of the system, but it would be interesting to also estimate or extract the damping parameter. Okay. Now, you may notice that although I have disturbed it with some amplitude, the amplitude is gradually reducing, and it will come to 0 after a while. But obviously, you may notice that there is some amount of damping in the system which is causing the amplitude to continuously reduce over a period of time. Now, the question here is, in this practical system, where is the contribution of damping, right? Because we discussed that there is a beam which has a motor mounted, that is the mass. There is a spring over here which is another element, the beam is hinged here. There is no dissipating mechanism that we see. There is no formal dashpot which of course is there, but we have not at the moment connected it to the vibratory system. So, the question is, where is the source of damping in this case, which is causing, now that you can see that the beam has already stopped vibrating. So, there must be some mechanism through which the energy of vibration is continuously getting reduced, and that questions the source of damping in this system. Now, one of the source of damping is the structural damping. So, if this beam deflects and undergoes strain, that cyclic stretch and compression in the beam is going to cause structural damping and the dissipation of the vibrational energy. But in this case, as we have seen, that there is almost remote chance of the beam actually bending and generating strain. But definitely we notice that the string is getting stretched and compressed, and no matter how small, but there would be some hysteretic or a structural damping because of the cyclic extension and compression in the material. So, intermolecular friction is going to create dissipation of the energy, and that is getting converted into heat. The other possibility is the position is the hinge, because the hinge is in the form of a bearing. Now, at the bearing again, because of the relative motion, there would be likelihood of some energy getting dissipated. So, the friction at the bearing location, however small it is going to create dissipation force or a damping in the bearing is going to cause absorption of or conversion of the vibration energy into heat. The other possibility and the third possibility, so this one could be a friction damping, because there is a relative motion. So, there depending upon how lubricated it is, there would be either viscous damping or there could be Coulomb damping if there is a metal to metal contact. So, this is one source, this structural damping is the other one, and based on the shape and the size of this motor, you may notice that as it keeps on swinging back and forth, you may also have a very little aerodynamic damping as well. So, there are various sources of damping mechanisms, but all of them in this particular example or a case, all these mechanisms provide very little damping, and that is the reason why you see that the amplitudes are not decaying so fast as compared to the other case, which I will show you shortly. Okay. Now, as I said, you may record this video, and then you can track how much is the period for maybe 10 oscillations or 20 oscillations, and from that average out the period of a single oscillation. That gives you the natural frequency. Okay. The other option that we have, which will not only give us the idea about the natural frequency, but also about the damping, is generating a time displacement plot of this vibratory motion. Okay. And for that purpose, what we have here is a pane that is fixed at the tip here, and a drum on the other side, as you can see, is rotating at a constant speed. Now, that drum has a graph paper on it. So, if we push the pane against the graph paper and let the system vibrate, it will trace out on the graph paper a time displacement plot. Okay. So, the amplitude versus time plot, and if we get that time displacement plot, of course, we can not only find the number of oscillations in a given period of time, but also based on the decay of the vibration, we can estimate the logarithmic decrement as we discussed. So, using logarithmic decrement, we can have an equivalent viscous damping coefficient, damping factor to be obtained. The drum is motorized, so it rotates at a constant speed. So, the graduations on the graph paper can be converted into time, because the drum moves at a constant rotational speed. So, what we shall now try and do is we will perturb the system the way we did it, and then trace a time displacement plot on the graph paper. So, we will perturb this now and then check, take couple of measurements. And you can see that after a while the amplitudes are getting diminished, and okay. So, that is the way practically one can do the measurement of the vibratory damping. So, what can happen is we show whatever data that we are getting is a combined effect of all the damping. So, that could be the damping at that point also. Okay, so this is how we perturb it, and we can record the time history. We can take couple of measurements here. So, what we saw is as the beam swings back and forth, the pen traces out the vibratory motion of that system. Okay. So, now what can be done is, because you have a graph of vibration amplitude as a function of time, you can pick up any number of cycles. Even the continuous 2 cycles can be used for finding out the logarithmic decrement. Now, the logarithmic decrement we all know is basically relates to the natural log of the successive cycles. Okay. So, either you take ith cycle with respect to I plus nth cycle, and this itself we all know is given by 2 pi zeta over 1 minus zeta square. Okay. For very small damping, this denominator therefore turns out to be close to 1 and therefore can be neglected, but if you want to be more accurate, maybe you can consider the denominator, compare it with this value. Now, from the graph paper which has traced out this time history, you can pick up this amplitude and maybe this amplitude. So, find out how much is this value and how much is this value, and then in that case there being 2 cycles completed. So, this n is going to be 2. If you want to account for more number of cycles, the error in the measurement can get averaged out, and in that case we get a better estimate of the damping in the system. So, this is what we are expected to do in this experiment, to find out what is the damping existing in the system. Now, having seen this sort of an undamped case, although there is damping, the damping is not coming from a dashpot, but from variety of other sources as I discussed. We do have a dashpot, a formal dashpot, which is like a cylinder filled with a viscous fluid, and then there is a piston that moves back and forth in this viscous fluid. So, I can bring in this dashpot into the vibratory system. So, apart from the mass and the spring, I now can bring a dashpot connected to it, so that our system truly then becomes a spring mass dashpot system. Okay. Now, having connected this dashpot, you would quickly realize the effect of bringing the dashpot in, and if I perturb this, so if I now perturb this and then release, you can see that compared to the previous case where the dashpot was not connected, you can see that the amplitudes are quickly getting back to 0. I mean, the amplitudes are becoming 0 in fewer number of cycles, much fewer number of cycles than it was in the previous case. I can do that very quickly for you. When this is connected, you can see that roughly about 6-7 cycles it completely dies out the initial amplitude, but if I disconnect it, you can see that the cycles, I mean the oscillations keep taking place. Okay, now having connected the dashpot, our system is now spring mass dashpot system, and as we see that the amplitudes are going to become 0 quick enough. So, I am taking multiple data sets here, so that we have an accurate estimate of the damping. Okay. Okay, so this is how we get the time displacement plot for the case when the dashpot is connected in the system. So, what you have observed is there is quite a heavy damping in the system, that is why within few cycles the amplitudes are coming back to its coming back to 0, and the decay is faster, and that is what the logarithmic decrement will be a larger value in this case. So, we will provide you these graphical measurements traced out on the graph paper, and from that you have to find the amplitudes and take appropriate number of cycles as is feasible from the short data, and then find out or calculate the value of zeta, the equivalent viscous damping factor.